Okay, first of all, I would like to thank you to the organizer for inviting me to this workshop. This is a joint work with Professor Maciesic, and I will show and present to you what we've done. We explored whether the Koopman operator-based data-driven algorithms can be applied to micropolar fluid dynamics. So I have a new verb, Koopmanizing. So here's the outline of the talk, just a few words about Koopman operator and associated algorithms. Then we will see how they can be applied to different dynamical systems like noisy systems and non-autonomous one. And then we will apply them to PDE and in particular to micropolar fluid flow. So we start as usual with nonlinear dynamics that could be generated by ODE and associate to it a Koopman operator. I denote it here with KT. But we start with the PDE, more precisely with an initial boundary value problem where the boundary and the initial conditions are defined. Then by using spatial discretization, we can obtain the ordinary, we can approximate this PDE by an ODE by using some of numerical approaches, finite difference, finite volumes, or finite elements, and obtain the corresponding ODE where the states of the systems are actually the values of the variables at these discrete time points. So this ODE, after solving, it gives us an dynamical system, which in practice usually, due to numerics, is discrete in time. So we obtain, we correspond to it a Koopman operator that is also discrete, and due to the fact that the application on the longer time series actually acts as the composition of the same short operators. We have one this small operator on small time delta t, which is actually some sort of generator of this semi-group. So, as Zlatko already said, if we sample the dynamics at the discrete time moments for obtaining the value of the observable at the future time, it we apply the Koopman, this Koopman operator k times, starting from an initial point x0. So if we know the eigenstructure of this Koopman operator, if we know the eigenfunctions and eigenvalues, which we denoted here by lambda j, these are these discrete time eigenvalues, we can examine we can determine the future values of the observable if we know its expression in terms of these eigenfunctions. So if this expression 2 is valid, then the future values of the observables at the time tk are obtained just by multiplying each term with this factor e to the k lambda j times delta t, starting from an initial point x0. Here, I will say Vj are actually the Koopman modes, and lambda g, as I already said, are eigenvalues. So what is the task of this DMD and other approximating operator? Actually is to construct, their task is to construct the low-dimensional operator that approximate the Koopman operator and capture the system's time evolution. So to determine and to evaluate more easily this evolution along time, it is it could be good to determine the spectral elements of this approximated operator. So what are our research questions? Our research questions are if we have the dynamics that is governed by PDE, for example, micropolar fluid dynamics, whether these algorithms will give a good approximation of our dynamics. The question that arises is if we will detect the dominant spatial temporal structure with good approximation. And what we have done in our work, we made reconstruction, interpolation, and forecasting, and we were interested in accuracy and stability of both. So the similar thing that Ella and Zlatko already showed. So we will use the dynamic mode composition. Since we come from the same Zlatko school, we have these algorithms that have old tools with residual computation and other enhancements that are done by him. And we will use it. So here is the setup. So we start with, we have two set of matrices. In the first one, we have the value of the observable f in time series of snapshots. In another one, the same, but just one step ahead. And we are looking for the task of the algorithm is to determine the finite dimensional approximation k that satisfy this in exactly or in a least square sense. So this k will be approximation of the projection of Koopman operator on this span of the columns of X. And we hope it will be low dimensional. It is low dimensional, and we hope if this k is good approximation of this approximation of this projection of Koopman operator, then we hope that the eigen information from K will approximate Koopman modes and eigenvalues correctly. So how can, as Zlatko already said, not all Ritz pairs are good approximation of Koopman modes, but we have this tool with residual evaluation, and by taking only those that have smaller residuals, we actually take only those that are good approximation, it could be good approximation of Koopman modes. The similar ideas of how to obtain this approximating operator are actually used in all these numerical algorithms like DMD, EDMD, van der Monde, etc. We use here this Zlatko's version DMD-RRR and also QR compressed version of this algorithm because it's much faster in some cases than this original version. So what we actually obtain from these Ritz pairs, as already said, for the all snapshots from this matrix X, we obtain its spatial temporal representation of the following form. So if we have a V and lambda J, then Fk, the column F, K column of X, is expressed in the following way. But from the algorithm, we do not obtain lambdas directly. So these are amplitudes of modes. They can be determined in different ways. Some of them are, some of the simplest is just projection to the first snapshot. So from the first snapshot, we project the first snapshots on the modes so that we obtain the coefficients are actually these amplitudes modes, these are lambdas. The second approach is to obtain alphas by using optimization and by solving this optimization task to minimize the error of each snapshot, the difference of each snapshot with its representation. So after minimizing it, we obtain the alpha in this way. So we tested both approaches on one of test example, and the results were similar on those that we try on. Here I just refer to a few works where original version of the algorithm and enhancement that we used here in our work are given. So actually all the tests that we done are referring, and in all tests we apply Hankel DMD, which means that we build the observable from time delay coordinates. In this way, we lift our dynamics in higher dimensional space and hope that some richer representation can be obtained, and also that this accuracy will be larger, and that better spectral decomposition will be obtained. So how this Hankel matrix is defined? If we take a window, that active window that is large W, and here P minus 1 is present time step, we take the value of the observables W times before, and determine and arrange them so that in each column of this matrix we have a time sequence of snapshots. And each column is followed by the column one step ahead, driven by the dynamics that we consider. So we obtain the matrix H, and now this matrix can play a role of snapshot matrix that we described before. So for X, we take first MH column, and for the Y, last MH column. One can observe that we can, for each active window, we can build different Hankel matrices with different dimensions. So in our work, we considered and compare what happened if we change the structure, the dimensions of this matrix, the number of columns and rows. And due to the previously described spatiotemporal discretization that we have, we can, by using 5, obtain reconstruction. So this data can be used for reconstruction, forecasting, and also for interpolation. If in this expression 5, take indices k from the active window, then we will obtain reconstruction of these snapshots. If we take k beyond this active time window, we obtain forecasting. And also we can use the 6 where we arbitrarily rearrange this expression 5. And this can be determined in this expression. T can be used continuously. We can use any T from this active window interval, not just indices, not just points. And we then obtain interpolation. We also consider how everything behaves. So these DMD algorithms and algorithms that we consider there are still some challenges. For example, noise. They are sensitive to noise. And for example, the problem is when the system is non-autonomous, since the Koopman operator is changing with time. So we consider here just briefly both cases. We take a signal, just simple sine signal, and add to it some noise, and want to see what happens, what will Hankel DMD gives to us after we apply it on an active window, which is here in gray color. We take active window of size 200, and I think I take Hankel matrix with dimension 150 times 50. So we determined just a simple DMD algorithm gives us 50 eigenvalues, which are obviously not all that are belonging to this clear signal. So the eigenvalue is equal to, if a linear frequency of this signal is 1/8, if we divide this by 2 pi. And if we want to extract just these two eigenvalues, so if we want to denoise the signal, there are two approaches that we try. The first one is to apply DMD-RRR with this residual evaluation. We take only the modes that have small residuals. I think the threshold, here I write the threshold is set to 0.05, and exactly those two eigenvalues plus minus 1/8 are obtained. These are the two red crosses. The second approach that we apply, we first denoise the signal by using total least squares rank algorithm. And then after the denoising process, we apply, for example, here I use DMD forward-backward algorithm. And again, I obtain just those two eigenvalues. These are with green, I think it's green crosses. So this is how the denoising could be solved. We see that the residual evaluation actually can solve it. Here you can see the prediction error. I did the reconstruction and prediction, the prediction error, and it is a smallest error is obtained for DMD-RRR. Here I also compared the two approaches for evaluating amplitude of modes, just projection to the first snapshots, if you remember, and optimizing long haul trajectory. And the blue one is mean and the standard deviation for 200 test repetitions there, which I obtained for prediction error when the first, and in the orange one when the second approach is used, and we can see that comparable results are actually obtained and also similar STD. The second problem that we consider is non-autonomous system. Here you can see that the matrix that drives this ODE is changing in time. So we have here changing frequency. And if we just naively apply the sliding active windows, we take an active window. We reconstruct quite accurate the signal, the results, but prediction is bad. This is due to the bad eigenvalues that we obtained. They should lie on unit circle. So the green one is the reconstruction, and it is good. This is the case in non-autonomous systems. So what can be done in this non-autonomous case? When non-autonomous system can be seen in a skew product formulation, for example, and if we can obtain a skew product formulation where the system become autonomous, then we can apply all previous idea on it. So here this could be done if we enlarge the dimension and define P1 and P2 in the following way. This is just another way to represent this previous system. And if we take a larger active window that captures all the changes of this dynamical all the main changes of this dynamical system, then the eigenvalues will be evaluated correctly and lies on the unit circle, eventually inside it. Prediction is very good, and the reconstruction, and also the prediction is obtained with high accuracy. And finally, I come to the PDE. So I applied why I use these two algorithms. First of all, noise will be by approximating numerically a different system, the noise will be introduced. So this is the first. And the boundary condition also will introduce some non-autonomous part. So these are two cases that can be solved with Hankel. So in the first case, we just take viscous-Burgess equation. This is an dissipative system with periodic boundary condition. We take just uniform discretization, the finite difference approximations, and apply Hankel DMD on windows large 200 with different dimensions. So we rearrange Hankel in different number of columns and rows. So we change numbers of columns. Of course, then the number of rows will be also changed accordingly because the active windows is always of the same size. And we can see that I did something. Okay. We can see that eigenvalues behave quite consistently. For larger number of columns, of course, more eigenvalues are obtained. But we can see here that the reconstruction error predictions are quite good. Here is the original equation solution, here the reconstructed and predicted. And you can see here the reconstruction and then at the end the prediction error. The reconstruction is almost great. The reconstruction error is bigger, but it is still acceptable. For larger number of columns, the results become better. Here, as I showed, the application of standard DMD, which is totally unuseful here, even for reconstruction and prediction tasks. Here I just averaged over space. So the reconstruction and prediction error, you can see that reconstruction is very good and prediction is better by increasing number of columns, it becomes better. I will skip this test example because I do not have much time. This is a chaotic test example where we show that the results are not good always. And now we come to the micropolar fluid flow case. It is obtained from classical fluid flow equation by adding the equation that describes the micro-rotation of particles. So we have one more equation that is describing this rotation and what happens in this case. Now the stress tensor that is in classical fluid symmetric is not symmetric anymore, and additionally coupled stress tensor appears and so on. What I thought that with micropolarity we will obtain we will obtain richer space of eigenstructures, but actually you will see that this will not happen. I consider here not a three-dimensional case, but just one-dimensional, the flow between two parallel plates, and a special case of flow where the flow is stratified into layers, and each layer moves with the same velocity and follows each trajectory, so that the problem becomes one-dimensional in Lagrangian formulation. So the trajectories are not these layers are not rectilinear, but in Lagrangian formulation, yes. And we set initial and boundary conditions here. We suppose that upper plate, that lower plate is fixed and upper moves according to some vector A of t in horizontal dimensions. We discretized this by a staggered grid, since we obtain a solution, that the numerics that is stable and accurate. We have some proof that actually the numerics converges. And we consider two test examples. The results are similar, so I will just comment for the first one. I take the one variable, this is density, that is obtained, and this is reconstruction and prediction. You can see that here the error for this reconstruction part, the error is very small, and prediction part we have some error, but it is quite useful. It can be used. I didn't say that the active size window that I used is 100 steps, and the prediction is 50 steps, half of this. So 50 steps ahead, not just one step, but 50 steps ahead. Similarly is the case for this is for the classical fluid. You can see here that the error is a bit larger than in a micropolar case, which I did not expect, but this is just another variable. This is theta that measure temperature. You can see that in both cases, for micropolar and for classical fluid, actually how this error depend on the number of columns in Hankel matrix. By increasing the number of columns, actually the error decreases. We can see that it exponentially increases with time. But lead time here is, as I said, is set to 50. So for 50 time steps, I evaluate this prediction. I show here just the eigenvalue, the imaginary part of eigenvalues that are obtained by sliding active windows. So you can see for micropolar case here on the left that they behave quite consistently and structured. For the classical case, which is here in the lower row, you can see at the beginning that some variation in eigens appear. I'm not sure why this happens, because I somehow expected that the micropolar case will be more, will have more variance in eigenstructure, but it did not happen. So the results for the second case is similar, and I will just escape because I'm on the end.
Thank you.
So yes, as Igor said in the beginning, we have a lot of open questions. We have, since I have the idea that I will somehow reveal this micropolarity in the flow, in the dynamics, this not happen, but it opens some new possibilities for further work. So thanks you.
Thank you.